So let us get back to the derivation of the black body radiation. So recall that we are assuming that we have a black body that is heated up to some temperature T. So our black body is heated up to, so the temperature T. Of course, with the unit of temperature that we are going to use is going to be Kelvin. And now, how can we think of the radiation in a heated up black body? Well, we can think of them as standing waves because they're in thermal equilibrium. So there are all kinds of different modes. And these modes are standing waves, and they will have different wavelengths or frequencies. Now the question is, how much energy do we associate with each mode? So how much energy do we associate with each mode? So the answer is given by a theorem in classical statistical mechanics called it's called Equipartition Theorem. And to derive the Equipartition Theorem result, we use a fact that was discovered by Boltzmann. And what Boltzmann showed us is that suppose we have some energy mode whose energy is between E and E plus delta E. Then what is the probability that that energy mode will exist, will be populated? And this is given, this is not normalized probability, and this is given by the Boltzmann factor. So the probability that our mode will have energy between E and E plus delta E is given by E to the power, this is the exponential, minus E divided by KBT, where KB is the famous Boltzmann's constant. So this is the probability given by classical statistical mechanics. So given this, we can say, okay, what is the average energy that of each mode? Well, we just reviewed the concept of averages. So what we will do is that we will, here, the energy is a continuous spectrum. So instead of a sum, we'll have an integral. So we have an integral which goes from 0 to infinity, and the average is E, and the probability that this will be populated is going to be E to the power E over KBT, and so D of E. And to normalize this, we divide by this integral, just the sum of all the probabilities. Of course, we are assuming thermal equilibrium, otherwise we could not use the Boltzmann factor. So now you have to do a little bit of integration, and what you can do is that to do the integral in the numerator, well, first you multiply by, say, KBT squared, and you divide by KBT. And what I'm doing is that I'm changing the integration variable to be, I'm defining some new variable called U, which will be given by E divided by KBT, and these are the prefactors you need to be able to do that. And once you do that, you will get something that goes to 0 to infinity, and you've got u here, and e to the power minus u, d of u, and then it's divided by 0 to infinity, e to the power minus u, d of u. And so now one should use the integration by parts for the numerator, and let me just remind you what that formula is. That formula is if you have some function of x, which is u, another function of x, which is v, then the integral is given by the integration by parts formula. And so you have u, and then the integral of v, and then you have the derivative of u, and an indefinite integral of v, and the whole thing is then integrated. So, you apply this to the numerator and you apply to the denominator, and what you get is that you get 1 in both. So the final result is going to be kbt. So this is the result. This is one version of the equipartition theorem. So it's called equipartition theorem because it means that every mode, independent of its energy, every mode has the same energy. So this is the equipartition